I'm building some microwave coaxial low-pass filters and need to fabricate the stepped core, so it's fixture time. Starting with a precise depth socket on a stable base, the filter core is built on a 3mm rod using 26mm discs of precise thickness and spacing. I made the aluminium spacers in the previous episode. The filter removes any harmonic distortion products from a high-powered transmission. It uses some convenient properties of a conductor inside a tube so that frequencies below a specified value pass through unimpeded, but higher frequencies are blocked. The geometry is beautifully simple, but it must be constructed with extreme care, hence the need for this fixture. Also, I love making fixtures, so what's not to like? As usual, AIMEE, my artificially intelligent machining and engineering expert, adds helpful hints and tips along the way.
I can also do excellent snark.
One of us just made a pin to fit the end of a 1.3 GHz high-powered low-pass filter and forgot they didn't have a collet small enough to grip the pin to turn the second end. Spoiler alert, it wasn't you.
Better make a custom collet then. Let's get on with it.
This is my gorgeous piercing saw from New Concepts in the USA. That's new with a silent K. I used to have an Eclipse saw 50 odd years ago, but this is much nicer to use. It's not the truly spiffy version with rotating blade clamps, but it's got lever tensioning and it feels great in my hand. Links in the description. I'm using Vallorbe 3/0 blades here. They're 0.24 by 0.48mm. That's 9 by 19 thou. Or milli bananas if you ask Curtis from Cutting Edge. They even do a titanium version now, but this is a total joy to use. It doesn't cut fast, but the teeth are tapered towards the end so you don't get any snagging near the end of the stroke. Normally I use these to make piercing cuts on thin sheet brass, but it eventually managed to cut slots about 30mm deep to form the collet. I cheated and clamped the brass rod vertically in a vise to do the rest of the cut and the cross cut. Not my best work, the slots are a bit wobbly, but for this purpose it's unimportant. It's rather like a clumsy medieval version of wire EDM. And no, AIMEE, I'm not talking about Skrillex or Deadmau5.
It works much better if you take the spike out first.
This This is one of the pins I machined in the previous episode. I'm holding it by the 2.1mm spigot so I can trim it to length, then turn a 2.385mm reduced shank back to a precise step in the 3mm diameter pin so it'll be exactly in the correct axial position. Gently touching the tool to the face of the collet and zeroing the DRO ensures my measurements are all relative to the datum face at the end of the 2.1mm spigot. My mailbox has been inundated by nearly 2 postcards from a Mrs. Trellis of North Wales. It reads, "Dear Adam, where can I buy the cutting oil that makes that lovely squelching noise?" Well, Mrs. Trellis, the link is in the description. Jargon busting time. DRO is digital readout, which uses an accurate electronic scale to report the position of the carriage and the cross slide of the lathe, and sometimes the compound slide and tailstock as well. It's dead spiffy and means I don't have to do any subtraction in my head. Time for a test fit. That seems quite good. Let's have a look and see how good. I was aiming for the middle of the tolerance range at 2.385mm. I reckon that's 1 micrometre under size. I'll chalk that up as another win for balanced cuts.
Hey Neil, what are you going to do with the other 11 pins where you missed the tolerance? Neil? Hello? You who? I'm not helping, am I?
Despite AIMEE's allegations, I hit the tolerance on all of the 20 pins to within +0 -10 micrometres. It's not too awful for a 40-year-old lathe with a rubbish operator turning 2.4mm OD pins from copper. Taking the final 3 cuts with the nose of the 0.2mm radius polished insert buried to 0.1mm each time provides a super level of consistency on this ancient cast iron lathe. I know lots of fine folks in the Keith Rucker fan club swear by spring cuts, but I swear at them. It's important not to have any steps at the joint between the end socket solder spill, the pin, and the central conductor tube. The diameter defines the characteristic impedance of the coaxial line, which needs to be 50 ohms continuously through the socket body and through the hole in the wall of the filter. The relationship's logarithmic. At this frequency with PTFE, air, copper and aluminium, it can be simplified without significant error to the square root of the inductance per unit length divided by the capacitance per unit length, as the dielectrics have near zero conductivity or loss and the conductors have extremely high conductivity. The clip that I'm talking over so rudely is the bottom end of the soldering fixture to hold the capacitive discs in place on the central rod. I'm drilling a through hole at 2.5mm to clear the 2.4mm end of the pin. One great way to help the channel is to click the like button. I'd be most grateful if you felt able to do that for me. I pushed things a bit too hard there and now all the chips are packed and welded together. Brilliant, well done Neil.
Hey, that's my script you're reading.
The next op's to drill at 3.0mm down to the correct depth with a step in the pin. The pin and the central rod locate against that edge. I'm using the tailstock DRO to set the hole depth a little deep. I'll set it to the final depth later by trimming the top rim of the fixture. Now I need to open up the hole to reduce the amount of conductive heat loss.
Hey Neil, have you ever thought about becoming a professional photographer? Might I suggest that you don't?
This is a prime example of setting up a shot really carefully, but then forgetting that things move.
Any competent YouTuber would reshoot that scene.
Any half-competent AI system would have warned me. As always with depth mics that have swappable probes, I'm calibrating it using a second class gauge block. This one's usually very repeatable and it looks spot on. You can guarantee that the first time I take it for granted though it'll be off by 10 microns and AIMEE will quite rightly scold me for carelessness. The relieved face is about 70 micrometers too deep, so that gives me some margin to take a little off the top edge if necessary. Next step is I'm going to put the pin in and then measure from the tip of the pin. I've already taken a very careful measurement of the distance between the end of the pin and the end of the 3mm step. However, that means I've got to do subtraction. So it only needed about 20 micrometers off. For those listening on monochrome sets, that's about a thou. The thickness of this part isn't critical, so I've flipped it in the collet. I'll face it off. A light chamfer and deburr with a Noga tool, and this part's ready to be drilled and tapped. Yeah, it's not a critical measurement, but I think that'll do. Huzzah! It's fixture time again. I found this lump of brass bar in my big box of random fixtures. It's already tapped M8 by 1.25, so all I need to do is face it and machine a 10mm diameter boss about 1.5mm high. In imperial units, that's halfway between a tad and a smidgen. My ancient pocket calculator tells me it's 3.7795275559/64, whatever they are. Well, that says 10 and a bit millimeters, so I'll take a finish cut and face off backwards, then take a finish cut on the face with a tiny undercut to remove the 0.2 millimeter radius fillet at the corner so the part won't get hung up on it. Now I need to machine the disc that forms the base of the soldering fixture. It's made from an offcut of 5x75mm flat aluminium bar. I marked the centre with a ruler across opposite corners and made a small punch mark with my excellent Starrett Auto Punch, details in the description. Centre drill first, then a Cobalt HSS 9.5mm stub and then a countersink. Then a long 10mm ream that I bought from Drill Service of Hawley. Apologies for the terrible phone footage, the light on my Bridgeport died and the battery for my horrible Sony camera also died. Again, as usual. You'll note that the plate is rather square. I want it to be round. That's what the brass fixture's for. Interrupted cuts on a part held only by friction on a way too small spigot. Great.
Comedy size M8 screw you have there. Great choice.
Now that is a proper rolling shutter artifact. Listeners watching on quadraphonic hi-fi systems may notice some run out on the face of the part. I'm going to ignore it. Now the disc's nice and round and no hospital visits nor any major shop repairs were necessary, I need to drill and countersink 2 holes to mate up with the M3 holes in the bottom element of the fixture. Yes, I know it isn't a countersink, it's a 4-flute carbide 45-degree chamfering tool, but I'm sure I can trust you not to report me to the authorities. AIMEE will probably give me one of her looks when she finds out. Next stop's drilling the M3 tapping holes. I'm using a 2.6mm drill because I don't want the threads to gall up or snap my tap. What on earth am I doing here? I've got a Tapmatic automatic tapping head and a perfectly sensible spiral point tap, and yet I'm doing it by hand with my gorgeous Starrett 93A wrench simply because it's a joy to use. Link in the description. And in the end, I had to put it in the machine vise anyway to complete the threading. Sometimes I wonder about myself. Earlier on I mentioned that the characteristic impedance of a coaxial line is the square root of the inductance divided by the capacitance per unit length. A more useful definition in terms of the diameters turns out to be just 138 times the log of the ratio of the diameters. I need to go into more detail on why that's the expression and how the filter design process works, along with a bit of the science, also soldering and testing the finished filters. That's all in the next episode, which will appear there once I make it.